Good afternoon, class. Last class, we entered the weird and wacky world of superconductors, which is a subset of the weird and wacky world of quantum physics and quantum mechanics, and that's actually something we're gonna talk about more about today, and I think again on Friday. Before we do that, and as you can see, I've got my liquid nitrogen and magnets and stuff up here again, so we're gonna get back. We're gonna get back into that today. But before we do that, I just want to quickly discuss two, maybe three electromechanical devices that I think are a good application that kind of wrap up some of the things we've been talking about in terms of electricity and magnetism. And so the first is something that we've been using all semester, and it's a speaker and a microphone. That picture you're looking at right now is a speaker or a microphone. They're the same thing. And they're a good example of the application of some of the electromagnetic things we've been talking about the last couple of classes. So we've been talking about electricity, then we started talking about magnetism, then we realized that actually they're two sides of the same coin, and a speaker is a good example of how we can take advantage of that. So here's how speakers work real fast, and it's pretty straightforward. So right now, I'm being amplified. I guess maybe I'm coming out of those two speakers right there. And, well, let's start with the microphone, just because there's one right in front of me. So let's start with the microphone. Here's what's going on. I am vibrating the air in front of me. I'm creating longitudinal pressure waves in a medium called air. This class, we don't really get into sound, so you can forget that part. But here's the part we do need to know. Attached to my tie is a little diaphragm that moves in response to the pressure waves in air. So as I speak, I'm expelling a gas. That gas has zones of high and low pressure in it. Those zones of high and low pressure are going to push on the little diaphragm inside that microphone. So that microphone is a little diaphragm that moves. Attached to that little tiny diaphragm are little tiny wires, and you can see them in that picture. So what you're looking at right now is a picture of a microphone, and on the back side of that diaphragm, you can see the little coil of wire. That little coil of wire has no current flowing through it. It's not plugged into a power source of any sort. It has no current flowing through it, but it is full of electrons. It's a wire. It's full of electrons just sitting there waiting to be pushed. And on the other side, not touching, but just nearby, you can see there's a permanent magnet. That permanent magnet does what permanent magnets do, and it's creating a nice magnetic field, just a nice constant magnetic field. It's not changing at all. However, when the diaphragm moves, the coil of wire that's attached to that diaphragm moves through that magnetic field. And the electrons in the wire feel that changing magnetic field. And as we've talked about, changing magnetic field is our source of electromotive force. In other words, gets those electrons going. And so the diaphragm moves in response to the sound coming out of my voice, out of my mouth. The diaphragm moves according to that. That moves the coil of wire, and that moves near a magnet. And so the current driven through that wire, current driven through that coil, is exactly proportional. It's a nice picture. It's a nice replication of the motion of created by the pressure waves in my mouth. And so I'll get current flowing through that wire, and it'll be sort of an alternating current. Sometimes the coil will be going towards stronger magnetic field. That'll drive current one way. Sometimes it'll be going away from the magnetic field. That'll drive current the other way. And on the other side, some device can be listening to that and capturing that data. And so I can actually capture my voice. My voice is oscillating pressure waves. That creates oscillating pressure waves in air. That creates an oscillation in the speaker. And that creates oscillating current. And then what I get out is a nice picture of what's coming out of my head right now. And so that's how a microphone works. It's just this very simple use of the idea of electricity and magnetism, the linkage between them. I can just take a coil of wire, attach it to a diaphragm, and boom, I get an electrical signal, a voltage that is an almost perfect replication of the wave that I'm creating with my mouth. And that's probably all we need to know about that. I don't know if you ever thought about it or if you ever knew this, but that's really all sound is. So when you're listening to a symphony of 100 instruments, I mean, you only have 2 audio receivers. You don't have a violin sensor or anything. And you can plug one ear up and you still can hear a symphony. And a symphony is just one oscillation. And your brain is just really good at going, oh, the clarinet just came in. And but it's just a waveform. It's a complicated waveform that your brain has gotten pretty good at deciphering, but it's just a waveform. And so I can take that waveform into an electromechanical device like this lapel mic, turn that into a waveform, a voltage waveform, and I've got my music. Then I can save it and email it to my friends or something. On the other side, on the speaker side, I'm just running that exact process in reverse. On the speaker side, I've got a diaphragm that wants to push on air. That's a speaker's job. Speaker's job pushes on air and creates sound waves. That speaker is attached to a wire that's near a permanent magnet. And all I have to do is take the sound that's coming through the system, or I can play music or whatever electrical signal. That creates a waveform. That waveform drives current, sometimes this way in the circuit, and that pushes and pulls on the coil because it's near a magnet. And so when the waveform is positive voltage, current goes this way. Maybe that will draw the coil and the magnet together. Then the waveform goes down. That drives current the other way. That'll push the two apart. And if you've ever watched a speaker, you usually can't see it because my voice is oscillating at 400 or 500 times a second. But if you've ever watched a speaker like in the back of the guy's car with the big 12-foot woofer and it's going boom, 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 those you can actually see because low bass is like 20, 30 times per second. That's usually visible. But that's what's all going on. The tiny little tweeter or the big subwoofer, I've got a magnet and a coil of wire. I'm driving current through there, and I can push and pull on it and create sound. So that's a nice mechanical device. Also, I think one of your homework problems that has to do with a nice application of the linkage between electricity and magnetism. Okay. Next, we've already talked about how an electric generator works. When Logan was up here riding the bike, Logan was spinning a magnet. So that's the picture on the left. Spinning a magnet past the coil of wire and driving current. So all of a sudden, Logan's breakfast became light. So that's an electric generator. Kind of like a speaker is just a microphone running in reverse. An electric motor is a generator run in reverse. In fact, I think what we had attached to Logan's bike was just a motor, but we ran it backwards and it became a generator. And you can do that. What else have we used as a generator up here? My little hand crank, I've used that one backwards as well. So a motor is just a generator run in reverse. So on the picture on the right, you can see AC power, like what's coming from the power company. I can plug that in to a coil of wire and pass that over toward a magnet. All of a sudden, that magnet will feel the north and the south. So like if I have my alternating current there, say the top becomes a south. The top of that C-shaped iron core becomes a south. That'll draw the north of the magnet, and it'll turn and be attracted. And then what I can do is as soon as that north becomes attracted, and it's in the position it's in right now, I can flip my alternating current. Then all of a sudden, I've got a north and a north, and they're going to repel. And so the motor will spin around over here. And then I can flip my alternating current. It'll be repelled and be attracted over here. And so all a motor is, an electric motor, is just that going on all day long. It's just an electromagnet pushing and pulling on sometimes on a permanent magnet. And I can push and pull and push and pull. And one of the reasons I want to bring that up, it's a good example of just, again, the linkage between electricity and magnetism, a good how things work that I think is a good example. But also, if you do think about it, these electric motors do come up a lot in our life. You walk into just about any environment these days, and that hum that you hear is some fan spinning somewhere, cooling some electrical device off. So my laptop has a little fan in it. It's constantly cooling it off. What am I hearing right now? I think the monitors have fans in them that are cooling them off. There's like 8 computers up here that are being cooled off right now. The fans that drive air around the building. Even the vibrate feature on your phone is a little DC motor, a little motor that spins around. CD players and the fan and the projector. Anyway, making things spin around is pretty common. And nowadays, we drive cars that way. So a Tesla just has DC motors in it. Electrical motors in it. And that's how an electric motor works. The simplest example is up there. I've got AC current just making a magnet that flips back and forth, and that pulls on a permanent magnet. There's other fancier ways to do it. Let's see. Here's a DC motor. A DC motor, if you just turned it on, it would flip once, and it would be happy because there's no AC current. So the picture I had a second ago, as soon as the motor becomes happy, you flip the poles on it, and then it becomes unhappy. It has to flip around again. Then you flip it again, and it has to keep going. And as long as you can stay one step ahead of the motor, you can keep it going. A DC motor, like when you just hook up a battery, which is not alternating, this motor up there is going to turn once and be done. So you use a clever setup. You can kind of see there, use these little contacts. And so those gray sides on either side of those yellow half moons are static, and those half moons go around with the motor. And so the motor flips around till it's happy, but all of a sudden the current flips. It's a DC motor. It's a battery, so the current is always trying to go the same direction, but which direction it's going in that yellow loop, it switches because of the contacts, so the contacts keep flipping. That's called a brushed DC motor, so there's these brushes that flip the contacts. Those aren't great because all that friction, all that contact eventually wears out. You get a lot of wear and tear, you get a lot of heat out of those. We've come up with more clever devices. If you fly RC planes or even RC cars nowadays, they're usually brushless DC motors, which use a different system. And then also a lot of the devices in our world now use an AC motor that doesn't require a permanent magnet. And so my picture there has a permanent magnet that's in the rotor. That's what's getting spun around. I can come up with this clever device. This is an AC induction motor. If you ever take apart your microwave, you'll see in there's a little fan. The fan blows air around inside the microwave. That is a picture of the fan inside your microwave. And notice there's no permanent magnets. So what it does is the AC voltage creates a magnet. That changing magnetic field actually induces current in those little kind of pinkish, orangish, reddish little, those are actually pieces of wire. It's just a little piece of wire. And so the changing magnetic field induces a current in that wire, which makes it a little magnet, and it actually attracts. And then the poles of the magnet flip, and it's repelled, and then it flips again, and it's attracted. It's repelled and attracted. And so you can actually get using AC current, you can actually get circular motion. You can actually make a fan, even ceiling fans basically do the same thing, or even like the box fan in your dorm usually runs on the same idea. Usually don't have brushes or anything like that. It's just an induction motor. Pretty clever little device. And then even more clever, and we don't need to get too much detail, you can see those other little coils of wire. See those two small vertical coils of wire? Those little coils of wire slow down the magnetic field just a bit. And so you get this kind of, rather than just north-south, you get a north-north, south-south, and you get this little step. And that's important for things like fans, because fans usually want to go a certain direction. And so you can always make sure your fan's going the right way and blowing air the right way. And then you might have a switch that flips that. But you can always be sure of that things are going to get going in the same direction. So all that picture you're looking at is just coils of wire and solid iron core. That's it, and a little rotor. But in that rotor is just solid iron and pieces of wire. So pretty ingenious little device. But notice when you turn if you have a nice ceiling fan, you can turn it on, it's almost silent. And because there's no contact. You've got your fan, you've got the part that's attached to the ceiling, that's static, and you've got the fan that's spinning around, and sometimes it'll get going crazy fast. There's nothing touching it. So it's being driven by non-contact, which I pretty neat that they do that. Just one other quick example, then we'll move on to that stuff. When I was in grad school, one of the research things I worked on was they want people that need like a heart pump, like a ventricular assist device. I don't know if anyone here knows anyone that needs a ventricular assist device, but some people's their heart's not doing its job, and so they need some sort of extra help. And so we were developing a pump to help pump blood, but your traditional pump has parts that touch, and you get shearing inside the blood, and that creates blood clotting. It's bad. So we were actually able to take something and make a little impeller, a little pump that just floated in a magnetic field. It didn't touch anything, which was pretty cool. And you could spin it up and spin it down, all just using magnetic fields, very similar to like your ceiling fan. And even cooler, because I've got a spinning thing inside a magnetic field, I can actually use that magnetic field to detect motion of the spinning thing. So I'm using magnetic fields to spin it. I'm also using magnetic fields to detect what's going on. So if the person all of a sudden jumps or lays down, we can quickly change the current to keep the thing floating inside a magnetic field. And so if you jump off something, you don't want the thing to bottom out and all of a sudden get blood shearing in the device. So anyway, lots of cool examples of playing around with electricity and magnetism. Okay, let's get back to magnetic levitation because that's fun. Last class we were talking about magnetic levitation. Here's a couple good examples of magnetic levitation. You may have seen that desk toy of like a little floating globe or pen or, I don't know, that Brookstone or something. They've got little things that float in magnetic fields. And nowadays, not so much in the States, but people that care about efficient transport have figured out maglev trains, magnetically levitated trains. Now, both of these examples I have up here, that fun little desk toy and maglev trains, are awesome because they float things in a magnetic field. That's really cool. But that wouldn't blow anyone's mind, I think, in the 1800s, even mid-late 1800s. The fact that you can magnetically levitate things, we've known that for a long time. So classical mechanics, classical physics can explain what's going on there. We've got little electrons running around creating a magnet. So the way a lot of maglev trains work, I mean, you can make a maglev train just with, refrigerator magnets. You just get enough of them, they repel each other. We know that. And that's what's, that little pencil trick on the left is just refrigerator magnets or something like that, creating a magnetic repulsion. So that's cool. We can make maglev trains. I don't know what else you can make with magnets. Stick things to your fridge. Cool stuff. It's neat that you can float things. But what's really nuts is what we started talking about last class, and what's the difference between kind of classical magnetic levitation or just magnetic attraction or repulsion and what we started dealing with last class is I don't have a permanent magnet, and I also don't have a source of current in either of those pictures. On the left is this is becoming now sort of a normal demonstration, floating a little disk or something on top of floating a superconductor on top of a magnet or vice versa. And then on the right is a picture of what we were playing with last class. That right there would blow the mind of someone in the 1800s because what we're looking at there involves superconductors. And superconductors might be the first way that in this class we kind of enter into the wacky world of quantum mechanics because superconductors shouldn't exist. So today I might get in a little bit of history, but here's just the quick 2 sentences of history. Maybe the history of physics largely has looked like periods that we've gotten to where we've said, good job guys, we figured it out, we know how the world works. Late 1800s, early 1900s, especially after 1905, 1915, after Einstein told us how gravity works, we had every reason to feel pretty good about our understanding of the world. And then right around 1920s, 1930s, all of that went out the window when we discovered the quantum world. And the quantum world is just a whole other set of physics that still to this day is very difficult to understand and is mysterious and a little bit mind-blowing. But superconductors are a good example of that. Superconductors from a classical perspective shouldn't exist. I shouldn't have a piece of material that has zero electrical resistance. I mentioned, let me pull this picture up. Here's a picture I pulled up last class. What we're used to is metals, as I cool them off, they become better conductors. That's normal. So the amount of atomic jiggling going on goes down the colder I get. That makes sense. That's the purple curve. That green curve makes no sense. That green curve, things get colder, getting better conductor, then wham, 0.0 resistance. That's crazy. And so today I want to talk a little bit more about why that happens and some other examples of that. Julia. Over the track, yeah. Oh, wow. I never thought about it. Julie asked about, when you go to the store and they swipe your card 50 times, it doesn't work. Then they take the grocery bag, and then it works? That's a great question. What is going on there? Yeah, it does seem to work. That's weird. Yeah, I guess. Let's see, what physics is going on there? Wow, that's a good one. What could possibly be going on in that grocery bag? You got me. That's a good one. I mean, it's just a plastic bag. That should not do anything. I mean, the only thing I can think of is like somehow maybe like the gap is too big and it just stabilizes it by reducing the tolerance in there. Like magnetically, it shouldn't be doing anything. That's a good one. That's a really, yeah, you stumped me on that one. Okay. Let's see. Let's do a couple. Let's play with it for a minute, and then we'll talk a little bit about what's going on there. Yeah. So yeah, let's just do a couple quick demos, and then gotta get, because that's the most important part, is playing with this stuff. Okay. So yeah, and while we're playing with this, hopefully I can start explaining some of it. And so I have some magnetic stuff up here, and then this is my superconductor that we played with yesterday. It doesn't look much like a superconductor, but what it is right now, it's there's a very, very thin sheet of superconducting material in here. So it's just a wafer of, I forget what the common one is yttrium, cobalt, barium oxide or something. It's just a superconductor. We found certain materials that do this. Inside here is one of them. And then what I also have in here is just some absorbent material to hold on to the liquid nitrogen, and then it's all wrapped in a piece of aluminum foil. So this is kind of a maglev train. The way we do now have maglev trains that use superconductivity. So one way to drive your maglev train is just using classical magnets. Another way to drive your maglev train is make the whole track like this. Make your whole track out of superconducting or not superconducting magnets, just very strong magnets. So make the whole track out of magnets, and then you have a superconductor on your train. The downside of superconductors is they have to be very cold. So I'm going to actually hold on to some liquid nitrogen. That's my source of getting heat energy out of here. So there's going to be some liquid nitrogen in the little absorbent material here. So let's do that. So I'll first pour some liquid nitrogen in here. So that's going to become my my train. So my train has to carry with it. My train has to carry with it not just the passengers and the train and all that. It has to carry with it a method of cooling stuff down. And the method that this train is using, it's going to actually have some liquid nitrogen on board in that little sponge. And so, yeah, okay, so if this was a superconductor, great. You know, say classical mechanics tells me that there's these things called superconductors. That's not possible, but say they exist. What classical mechanics would say is when I take this out and I put it near one of these magnets, like this little square here is a magnet. We'll use that first. So is that on camera? There. So this square here is a strong magnet. So what classical mechanics says is when I bring this closer to that square, the changing magnetic field, the fact that I'm bringing it closer, will induce currents in the superconductor. And that will create a magnet that will oppose it. There's two things about that picture. That's the classical picture. That's Lenz's law that I think we discovered, I don't know when Lenz was, 1800s or something. What Lenz's law doesn't tell me is that I don't have to actually change it. I can't do it with this setup here. Yeah, I can't do it here. Tempting. But what I could do is I could actually place the superconductor on this magnet, and it would just sit there when it was warm. And I could pour liquid nitrogen over it until it got cold enough. It would actually just pop up. So it actually would expel the magnetic field. And that's crazy, and only quantum mechanics can tell me why in the world that's happening. And even cooler than that, so just this thing expelling the magnetic field that's within it. So that's what's going on. There's a magnetic field passing through it. It drops below its critical temperature, and all of a sudden, boom, the magnetic fields leave. That's wacky. Even wackier is the fact that I've made my superconductor so thin, this guy right here, that some of the magnetic fields will poke through. Some of the magnetic fields will poke through, and when they do, I get what's called, let's see if I can see that in the camera view. I get what's called flux pinning. And this thing is a very stable equilibrium. This is in a very stable position. I can tilt it to one side, it wants to stay that way. I can tilt it to the other side, it wants to stay that way. Wherever I put it, this is called flux pinning. Oh, I can even do that. Wait, there it is. Yeah, on camera, okay. And what's happening here is little bits of magnetic field are actually poking through my superconductor. And that is a state, it creates a, that is what the superconductor doesn't want to change. So once the flux lines poke through there, and it takes force for me to do that. I have to force it into a position. But once I do that, those flux lines want to stay put. And the superconductor will do what it can to keep those flux lines stationary by running little superconducting currents through there. And then I can do the same situation here. And because it's curved, it'll just kind of float back and forth, which is pretty cool. And again, I could probably tilt that, and it's going to keep doing that. And so I'm hoping someday in our lifetime we drive around on little trains that float like that. So let's see. Let's cool it off a little bit more. So while that's cooling off, let's see if we. Oh yeah. So we have to talk about. Well, yeah. It's actually I mean, if you wanna switch your major right now and become a physics major and study superconductors, you can do that because we still don't quite know what's going on in here. But whoops, I knew that was gonna happen. That's so okay. I think I could probably do this. Yeah, there we go. And so last class, this table was flipped upside down, so the magnets were on top, or I guess right side up. Today, it's upside down, and I can still get this little guy to cruise around. So the magnets are on the bottom, and I don't know if you can ever see in the camera shot. He's a good centimeter or two away from. He's just hovering below here. And so again, this is called flux pinning, and that it takes a little force for me to put it into a certain position. But once I do, the superconductor wants it to keep that flux position. Now, I guess one other detail I could mention about this is, I'll wait till it comes around again. In this setup, the magnetic field is constant in this direction. That's why it can flow in that direction with no resistance. With this rectangle here, there's no place it can really go that is constant, and so that's why I can move it around, and it's going to want to stay put. There's no place where the magnetic field is constant, so it always wants to kind of stay in the position it's in. But for these other two setups, the magnetic field is constant in this direction, so it's free to go in that direction, but not side to side, and kind of same here, where the magnetic field lines are set up in a way on these devices where I kind of have no change in magnetic field this way, so there's no resistance to motion in that way. Okay. So I'm going to cool this off one more time. I think this will be one of those things that everyone at the end of class should come up and take a close look, especially this one. It's just a little bit mind-blowing just to see something. These tongs are metal. Okay, it's a little mind-blowing to see something just sit like that, a solid, that's like 1.5 inches off the surface of that. That's just weird. Okay, so at the end of class, everyone should come look at that. And yeah, I wouldn't touch it because this is a $1,000 superconductor, but you can at least come look at it. Okay, so let's take like, we've 16 minutes. Let's take like one more minute to talk about, maybe I'll pull that down right now. Well, actually, I'm going to leave that there. What he should do as he warms up to his critical temperature, you'll just see it sit down in a minute or probably 5 minutes. It'll probably just sit down. It'll be a nice, simple transition. Or I could even put, yeah, I'll do that. I'll leave him there. Okay. Let's see. So real quick, here's what's going on inside a normal conductor. In a normal conductor, you've got electrons floating around. Electrons are bits of matter. They behave like all matter. I think I mentioned this last class. Like, fortunately, you and I are made of stuff called matter. Technically, you and I are made of that stuff. So you and I are made of, well, the stuff on the left, the green and the blue ones, that's what you and I are made of. You and I adhere to what you might call normal physics, that we can't be two places at one time, we don't fall through our chair, we take up space. Like, we exhibit normal physics, and electrons do the same thing. So electrons flowing through a material exhibit normal physical behavior. They bump into things, create heat, blah, blah, blah. We're familiar with all that. All the stuff that classical mechanics tells us. inside a superconductor, we get a very weird situation, and I don't think I have a picture of it. I don't, so I'll just have to very quickly. Well, here's my picture. There, that's what's going on inside a superconductor. Yeah, that's what's going on. Yeah. So we're getting Cooper pairs. That's what all that math was about. So yeah, that was the best picture I could find, really, because it's hard to explain. But here's basically what's going on. Inside a superconductor, we know that electrons are both negative. They repel each other. They don't want to be near each other. They're flowing through, as I've described before, metal can be thought of as just like a lattice of positive ions. The electrons are flowing through. As they flow through, an electron might pull in some of those positive charges, right? Opposite charges attract. So the electron, as it flows through, might pull in a couple of the positive ions toward each other a little bit. And what will happen is they'll actually create a little area of positive charge, of net positive charge, because that electron going through kind of pulled in some positive charges. Those positive charges will attract the next electron. And what can happen sometimes below the critical temperature is that attraction, there's another electron, that electron's attraction to that little area of positive exceeds the repulsion to the other electron because negative charges repel each other. And so I get a setup where there's a battle going on. These two electrons want to repel, but also this electron created this little area of positive, and it wants to be pulled in. And what will happen is the two electrons pair up. That's kind of cool. So I get this little pairing. But here's the crazy thing that happens. When electrons pair up, they stop adhering to normal physics. And what we have here, the green and the blue on the left, those are called fermions. Fermions, named after Enrico Fermi. Fermions adhere to Fermi statistics, Fermi physics, Fermi-Dirac statistics. They adhere to normal physics. Two electrons together can act like a boson. Those are the red guys on the right. Now, today I'm going to mention a lot of ons. We already talked about photons and electrons. There's bosons and hadrons and mesons and leptons and gluons. There's a lot of ons, so we're going to learn some of them today. Two electrons are fermions. Well, electrons are fermions. Two together become a boson. Here's what you need about bosons. Bosons don't care about normal physics, and they adhere to a completely different set of rules, Bose-Einstein statistics. And so I can get electrons to pair up and become a boson. Bosons, once that happens, yeah, all bets are off. I am now adhering to a different set of physics. I fly right through that conductor, zero interaction with the fermions around me. And I get this just really wacky setup. And again, physicists still today struggle a little bit with some of the details of what's going on there, but that's probably for us all we need to know, that I can get electrons, which are fermions, to behave like bosons, which is wacky. That's the short of it. Okay. And I think that is a good segue into, I think that's a good segue into what I want to talk about next. And what I want to talk about next today and a little bit tomorrow, next class, is how we find these guys. And so I think on the first day of class I mentioned we physicists now think that the world is made up of these 17 particles. How do you find a fundamental particle? Well, starting way back when I think J.J. Thomson or Rutherford, I always forget, I think J.J. Thomson discovered the electron. Yeah. One of the ways that J.J. Thomson probed the subatomic world was by crashing particles into each other. You might think of him as one of the first particle physicists. They probed matter by crashing matter into each other. That's still the main way we do it. And let's see, let's talk, I think that's a good way to go. So here, we've been doing that for a long time. We've been doing that since the 50s. Since the 50s, the way we have probed the universe, the way we have probed matter, is by smashing particles into each other. You may have heard of particle colliders or particle smashers, atom smashers. That's what we've been doing for the last several decades, and it's still a good way to go. Until 2001, I think it was. Yeah, I forget, 2001 or something. No, it was later than that. It was until 2008 or 9, the United States had the biggest particle smasher. It was at Fermilab in Chicago, and it was called the Tevatron. And the Tevatron sent particles around at 1 TeV, 1 tera electron volt, hence Tevatron. And we had this Tevatron, it was amazing, and we sent electrons and anti-electrons, positrons, around and smashed them into each other and got a lot of data and discovered a couple of the particles that are up there. Also in the US, we have SLAC, Stanford Linear Accelerator. It's just a big tube, and we smash things into fixed targets. We discovered a couple of those at SLAC. I forget which one. I think maybe the top or bottom quark. Then when it flipped on in 2008, and still now, the largest particle smasher in the world is the Large Hadron Collider. We have 8 minutes left. Let's talk about the Large Hadron Collider for 8 minutes, and we'll start with an eye clicker. Let's do that. Pardon? No. Sorry. Okay, let's start with an eye clicker. We have 8 minutes left. I have 3 eye clickers. We're going to go through real fast. So here's the Large Hadron Collider. That's just outside Geneva at CERN. CERN is the Center for European Nuclear Research. It's 17 miles around. I would like you to take a stab at how long does it take a proton, that's what they accelerate, hydrogen nuclei. How long does it take a proton to go 17 miles? So, you know, just for perspective, it would take you, what, 17 minutes to drive it? How long does it take a proton? About a minute, so 17 times faster than your car, or even faster than that. B would be a second, C would be 1/10 of a second, and D is 1/10,000th of a second. Let's take 6 more seconds, because like I said, I have 3 of these. Both are still coming in. 5, 4, 3, 2, 1. Okay. So what you're seeing in that picture, which is not terribly clear. Let's make it bigger. Wait. Where's my? There it is. What you're seeing in that picture is the accelerator complex at CERN. The accelerator complex at CERN is complex. You can see it right there. Start the protons here. It starts with something called LINAC-2. It's a linear accelerator. They subject hydrogen to a very strong electric field, and as we now know, that's how you separate the positive nucleus from the electron. So then they're left with just a proton. So hydrogen is just a proton and electron. Yank the electron off, you've got a proton. They send that down LINAC-2, just subjecting it to a very strong electric field. And by the time it leaves LINAC-2, it's going about the third the speed of light. Then they send it through a couple other accelerators, the proton synchrotron, the super proton synchrotron, and then finally into the Large Hadron Collider. By the time it goes into the Large Hadron Collider, you can see it is going 99.9999% the speed of light. And it goes around this 17-mile track 10,000 times a second. So it goes 10,000 times a second. So the answer is what? D. Answer's D. So it's going around that track 10,000, actually around 11,000 times a second, or 1 lap every 10,000th of a second. That's insane. And so they have computers and machines actually doing that. It's mind-blowing that they can get something going that fast. So we get stuff going the speed of light, which is nuts. We take physical matter and accelerate it to the speed that traditionally only light can go. It's kind of nuts. Okay, let's do another eye clicker. Here's, again, the Large Hadron Collider. And by the way, 2 reasons I want to talk about the Large Hadron Collider today in next class. One, it's the largest science experiment ever made. It is the forefront of all physics in the world right now. A lot of physics in the world right now. It's also such a cool example of so many of the phenomena we've talked about, including superconductors. So the magnets at CERN, and we'll talk about why you need magnets to build a Large Hadron Collider. The magnets at CERN are superconducting, and they've got them all wrapped around that 17-mile track. And so, whoops, here we go. I want to know how much wire is in there. So it's 17 miles around. There's wires all over the place. We have enough superconducting wire inside the Large Hadron Collider to either A, stretch across the Atlantic, B, go all the way around the circumference of the Earth, C, to the moon and back, or D, to the sun and back 6 times. Let's take 15 more. Question. Right. That's great. Yeah, when it was turned on, there were some scientists actually, not just total crack. Well, yeah, there were crackpots, but not, you know, they had degrees from somewhere. They sued CERN to try to get them to stop because physics tells us you smash two things together strong enough, you can create a point. So with such density, you've created a black hole. And a black hole could eat our entire planet. And so maybe they were going to create a black hole that would suck the whole planet into the black hole. Our current understanding of physics is that those black holes would be created and would evaporate immediately with no risk to humanity. You know, of course, there's like this tiny, tiny part of your brain that's like, what if there's something we don't know? So there was a little bit of a, like, flip it on, like, is this going to work? But for the most part, we're pretty sure it was going to be safe. Yeah. Okay. Great question. So question number 2, you might figure out after this second question, might lead you to get the next one right. The LHC is just all about superlatives. It's the coldest place in the universe. It's the best vacuum in the universe. And the amount of wire inside the Large Hadron Collider is actually enough to go to the sun and back 6 times. Bonkers. And that's superconducting expensive wire. That's a lot. And we'll talk about, I guess it's going to be next class, why we need so much. Let's do one more eye clicker for fun, and then we might have to wrap it up. Yeah, people, you're not even going to read it, just D. Yeah. So, yeah, people, I don't even think people read it. So, here's what's going on. Here's what's going on at CERN, and then we'll just get into some more detail next class. So, they smash these particles together, and they take pictures. They've got these big digital cameras, essentially, and they take pictures of the data. The data coming out of CERN in a year, if it was stored on CDs, would make a stack of CDs 12 miles high every year. So it's a crazy endeavor. It's a whole list of superlatives. It's bonkers. We'll talk some more details about it on Friday.